Hi, my name is Scott Edwards and I'm the Chief Operating Officer here at entX. I'm responsible for the development and commercialisation of our targeted products in entX's space and defence pillar. Our two products closest to commercialisation are our beta voltaic power generator, what we call GenX, and our Lunar survival technology, the Radioisotope Heating Unit, or what we call RHU. entX's Radioisotope Heating Unit, or the RHU, is a technology to survive the lunar night. One of the most fundamental constraints in lunar operations today is simply surviving the lunar night. A lunar day-night cycle is about 28 Earth days, with around 14 days of continuous darkness. During that period, temperatures drop to around minus 190 degrees Celsius. At those temperatures, batteries fail, electronics shut down, and most payloads are effectively lost. What we see today is a hard limit. Missions last about 10 to 14 days and then they end. Surviving the lunar night has been identified by NASA as its key capability shortfall for lunar exploration. But the entX RHU is designed specifically to solve that lunar night constraint. Instead of storing energy like a battery, it continuously generates heat from radioactive decay. That heat is used to keep systems within their operational temperature range. We're not trying to power the system, we're trying to keep it alive with heat. So what's different about the entX RHU? What differentiates our RHU is how we've approached isotope selection and system design. We've avoided plutonium-based systems and supply chains which are scarce, highly regulated and not commercially accessible. Instead, we've leveraged isotopes from established nuclear medicine supply chains. This significantly reduces regulatory friction and improves the ability to scale. This is about making RHUs commercially deployable, not just technically feasible. So this impact is quite significant. We can move from missions lasting a single lunar day to potentially months or even up to a year. That fundamentally changes mission economics and architecture. You're no longer designing for survival, you're designing for persistence. You're also increasing mission lifetime. So how do we validate an RHU? The team has developed a demonstrator 3U lunar payload, which incorporates our RHU, our thermal management system, and a thermal switch. We've also developed the radioisotope fuel pellet at ANSTO's OPAL nuclear reactor in Sydney, confirming our simulations and our thermal studies. The fuel does produce good heat. We've also undertaken numerous tests, ballistics testing, thermal vacuum, vibration and durability. The intent is for this 3U demonstrator to validate our 1-watt RHU system. Our thermal modelling and analysis shows that the 3U payload demonstrator can survive up to 6 lunar nights. That's a huge change from the current 10 to 14 day limitation. We've also started working with lunar lander companies and payload developers, such as iSpace in Japan and Australia's very own Fleet Space. With the Australian Space Agency as well as the South Australian Government, we've undertaken detailed engineering feasibility studies with these companies to determine what it would take for our RHU to get their systems through the lunar night. With these studies, we've shown that the RHU can successfully take these payloads through the lunar night and beyond. What's also commercially important is that we've shown that incorporating our RHU translates directly into cost savings, reducing launch mass and saving on the order of $1 to $2 million versus battery-based systems, and that's only on 1 watt alone. At the moment, we're currently progressing towards flight heritage. We're targeting a US-based suborbital launch with payload recovery. And while that flight heritage is important to get excellent data, it's really what it takes to get to that point, the nuclear flight safety process. No private company has undertaken this successfully, and at this stage it's only been the US government that has done so. The nuclear flight safety process is being undertaken by a US national lab. This lab is renowned for this type of work, having done plutonium-based assessments on NASA's RTGs. What's important is that this technology scales. We've assessed systems from sub-watt through to multi-tens of watts. It supports everything from small payloads through to lander subsystems. At higher power levels, we're seeing mass reductions of 2 to 5 times compared to battery heating solutions. This makes lunar night survival possible. The takeaway here is simple. RHU doesn't just extend missions, it enables entirely new mission architectures.